Hi everyone, I hope that you are having an awesome day so far. I'd like to welcome you to freemathhelp.ca. If you have never joined us before, we are here to help you with your questions about anything pertaining to grade 11 math, or if you might have something from other grades before grade 11 that you want us to review in order to help you with grade 11 math. That's what we're here for. And what happens every week is basically I end up doing a lesson, and each week we do different lessons based on the units that are part of the MCR3U curriculum, which is the grade 11 functions course, and it pertains also a lot to the grade 11 UC course as well, so people in both of those courses can benefit from watching. What we're going to look at this week are more areas pertaining to trigonometric functions and understanding the identities that you do need to really have a good grasp on in order to do well in this course and to do well in grade 12 math as well, in the grade 12 advanced functions. So without further ado, we're going to get started. Last week and the week before, we started on the more preliminary aspects of this unit, and now we're going to get into some of the nitty-gritty, as we like to say, of how everything works and how we can apply it to various questions that we might get on tests or assignments. So, like I said, if you're just tuning in, we are here to answer your questions. So whether it's a question that has to do with what I'm talking about, or if it's a question that has to do with some other unit, that's totally fine. You can feel free to leave those questions in the YouTube chat. And without further ado, we're going to get started. So last week we talked a little bit about identities and also a little bit more on how the unit circle pertains to the various identities that we discussed. Now, this week, what we are going to talk about is a more in-depth understanding, or we're going to gain a more in-depth understanding of what it is that all of this stuff really means. So I'm just going to move this over here. Okay, so for those who were here last week, you might recall that we talked about the unit circle and how it really relates to everything and all of the pieces of trigonometry. Wow, sorry. Clearly I've been talking for too many hours today and I don't have enough caffeine in my system. But that's okay. I will trudge on. I'm a real hero like that. Just kidding. So, okay, got X and Y. So for those who were here last week, you might recall that we talked about how we use our identities to solve questions such as this. So let's say we had a unit circle, and again, let's say that this was a really cool unit circle. Let's pretend that I drew that really nicely, you guys. Just give me the benefit of the doubt in terms of my drawing skills here. And let's say that we're talking about, we're working on these drawing skills, you guys. We're trying to get there. Okay, so there we go. We've got that. And we were talking about how the identities that we learned in grade 10, the SOHCAHTOA identities, have to do with the unit circle. So if we recall, this is y and this is x, obviously, as we know from being in math all these years. And this is the radius. So obviously this is the radius because it's half of the unit circle. And what's really going on here is that we're saying that we have an angle right there, and we want to use the identities to solve for that. So what we're going to start with today is understanding the reciprocal identities. So, we've learned up until now all about SOHCAHTOA. We've got sine, theta, and we've got cos of theta, and we've got tangent of theta. And we know, based on everything we've learned throughout the past few years of high school, oh my gosh, I keep pressing the wrong button. There we go. So what we've learned over the past few years of high school is really that obviously we can solve for either side lengths or angles using these formulas in various methods in applying them. And what's really happening here in this unit circle is if I was to solve for the sine, for example, of this angle, this theta right here, what would happen is I'm actually solving for the, and if we remember our SOHCAHTOA, So, ka, toa. What's really happening in sine is that I'm asking for the opposite, which is y, over the hypotenuse, which is the radius. And one way that we were indicating that last week, which is a more new concept that we learned, opposite over the radius. Oh, hypotenuse is what I'm trying to say. Goodness. And then for cos of theta, it's the adjacent. So in the cos of theta, it's x over r, because that's adjacent over the hypotenuse. And here we've got tan of theta, which is opposite over adjacent, and that's y over r. So what we're going to learn about today are some cool, I say cool because math is cool in my opinion, but I know not everybody feels that way about it. But we are going to learn about some very interesting changes that we can make to these identities to make them a little bit more, I would say useful, I guess. I don't know exactly how you could put it, but yeah, so what we're going to, and when I say changes, I mean we're creating different and new identities, but that pertain to these. So what we're going to talk about today are these identities. If you look right here in the corner, you'll see my little star, the reciprocal identities. And the reason that these are important is because sometimes we are given questions that pertain only to, and I keep saying the word pertain, but that really have only to do with the reciprocal identities. And we need to understand how they work before we start doing trig identities where they have to equal each other and we have to solve them, because otherwise it's very, very difficult to understand what the heck is going on. So we know that when something is reciprocal, that means that it's the inverse of what we originally were looking at. So for example, 5 by itself, and then if I was to ask for the reciprocal, it would be 1 over 5. So just as you can see here, we have secant, which is the reciprocal identity for cos. So for that, we have secant of theta equals 1 over cos of theta. And if we know that the reciprocal is what's really happening is the fraction is being flipped, then in this case, if we know that cos of theta is x over r, well then the reciprocal, or the secant in this case, the secant of theta is actually going to be r over x. And we can do the same thing with sine. Sine has a reciprocal identity as well, and that's cosecant of theta, CSC. And I've always thought this is so dumb that instead of just making the letters the same, like cosecant, blah, 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 they have them reversed. I don't know what genius came up with that, but just something to remember. Most teachers will actually give you your formula sheet on tests, so that's good, but just depends on your teacher, I guess. Okay, so as we know, this is obviously a reciprocal, so in order to demonstrate that reciprocity, we do the flipping of this here. So in this case, it's r over y. And finally, we have cotangent, which is COT theta, and that's 1 over tan of theta. And that is going to be r, oh, in this case I wrote this wrong, or I just didn't draw it properly. Opposite, yeah. So this is going to be x over y. I highly recommend writing these down if you're following along, just because sometimes teachers don't give them out like this so concretely. This is something that I've kind of noticed over the years and just found that writing with my students was really helpful. What I do want to quickly do here is demonstrate why we are able to flip these. Okay, so if we know that a reciprocity or a reciprocal identity is the flipped fraction, then for example, if we have cotangent of theta, and cotangent of theta is 1 over tan of theta, and I know that 1 over tan of theta is like saying 1 over y divided by x. Well, what's really happening here is that I'm saying 1 divided by y over x. And when we have a division for fractions, we know that what's really going to happen in order for us to solve this is that we're going to actually turn it into a multiplication by flipping the second fraction. And therefore, we get our identities. See here, this is the same as this. This is the same as this here. Okay, so hopefully this is kind of just a primer for everything we're going to talk about today. I hope this makes sense for you guys. If any part of this is going over your head and you're wondering what the heck I'm talking about, feel free to leave a question in the chat. I'm happy to elaborate. I just don't want to elaborate if everyone's cool with it and then bore you guys to death. So again, if you have a question, I know this stuff is kind of complicated, so you're more than welcome to leave one in the chat and I'm here to answer those for you. Okay, so also I'm trying to speak a little bit louder this week because I noticed in the recording last week that the grade 11 class was a little bit quieter. And I think it's because of my computer fan being a little bit louder. So hopefully you can hear me and I'm hopefully not like deafening you with my talking. So as we start to learn these identities, the way that they become applicable to our math questions is that we actually will be given questions where we're solving using this information. So sometimes you'll get a question like, you know, what is the cosecant of this angle that we've already given you? Or yada, yada, yada. So I'm going to explain what I mean by that. So let's say that we have a triangle that looks like this. Wow, I don't know why I'm not using my straight line generator here. There we go. That would be smart of me. Okay, so say I have this triangle. Oh gosh, that was not a very straight line, was it? Kind of like that. Okay, so I have this triangle here. Let's pretend those lines are perfectly straight. And I know that it's a 90-degree triangle. And again, these reciprocal identities really do only pertain, just like the original ones, to the triangles that are 90 degrees or have a 90-degree angle, so a right angle triangle. And what we're doing here is we're basically saying that this angle right here is 65 degrees. And let's say that this side length from here to here is 30 degrees or 30 meters. Okay, so if I've been given all of this information and I'm asked to solve for cosecant of 65 degrees, there are a couple methods that you can use to do this. And one thing I want to recall, or I want you guys to recall, is that obviously in some of these situations we need to solve for things so that it'll make a little bit more sense. So in this particular situation, what we're looking at is we've got the opposite. This is the opposite of 65 degrees. We don't have really any other information, so not much is helpful to us. And in this case, we've got 30 over the length, or the L, which we'll call this, but I'm just going to call this the hypotenuse, because that makes more sense. So 30 over the hypotenuse is equal to the side that's opposite over the hypotenuse. Because obviously 30 is the opposite side. So in this case, we know that this identity is equal to sine. So let's go ahead and solve in that sense. So we've got 30 over the hypotenuse equals sine of 65. And in this case, you're going to use your calculator and you're going to get the sine of 65 because it's not one of those angles that we have a perfect answer for. And make sure that your calculator is in degrees because we are in grade 11 and we're using degrees. Oh, there we go. So sine of 65 is equal to 0.9063. And we've got this here. So let's just go ahead and solve for L. So we know that this is going to change to 30 over 0.9063 equals L. So we can solve our side length as being 33.1. So that's this hypotenuse here. We've got 33.1 as our hypotenuse. So given that we know that cosecant is the inverse of sine, well then all we need to know is basically that instead of doing opposite over hypotenuse, we're going to now do hypotenuse over opposite. So let's go ahead and do that. And hopefully this is making sense for you guys. If it's not, we can definitely try another example, okay? So in this case, it's going to be hypotenuse over opposite. And all we need to do is plug that in. And we've got the ratio here. And then basically, that's going to equal 1.103. So this is the answer. We've got this here. Now, let's say they gave you this information and they said solve for sine of 65 given the cosecant of 65. Well, let's go ahead and do that. If I know that the cosecant of 65 is equal to 1 over the sine of 65, well then let's go ahead and work our way backwards. So in this case, I've got 1.103 equals 1 over sine of 65. And then all I need to do is isolate sine of 65. So first I'm going to multiply it up here, and then I'm going to divide off 1.103 from both sides, and then that's going to be sine of 65 equals 1 over 1.103. And if I plug that into my calculator, I get the original answer that I had for sine of 65, which is 0.9063. Okay? So this is this, like, in my years of tutoring, every single year, even though this is stuff that like teachers usually kind of do at the beginning of a unit, I found that throughout every trig session that I would do with a student, oftentimes questions like this would come up over and over again, and people were really confused by them. So I don't want you guys to get confused by the extra letters that are in this scenario. It's literally algebra, and if you just apply your algebraic information properly, you're going to get the right answer. Okay, so hopefully that makes a little bit of sense. We're going to move on a little bit, but if you have questions regarding the stuff I just talked about, feel free to drop them in the chat, okay, and we can go over that stuff. Okay, awesome. So moving on here, well, we have that information, and obviously it's really important to understand how to kind of flip between all of these things and how all of this information is condensed when it comes to doing tests, because obviously you guys are going to be tested on a lot of this stuff, and this stuff does not go away in grade 12, my friends. Like, I'll show you what I mean. This formula sheet that I have right here for you on the side, this is actually a grade 12 formula sheet, and it's the MHF4U formula sheet. It actually is something that's going to continue on for the rest of math. If you take calculus, you do need to understand these things. Depending on which calculus course you take, it actually really is important that you get this stuff on a deep level. And when I say depending on which calculus course you take, I mean at the university level. Like if you take calculus in university, there's different calculus courses for different streams of learning. So for example, I've taken both a biology calculus course and a business calculus course, and even though a lot of the fundamental concepts are the same, the biology calculus course really required me to understand trigonometry really well, and the business calculus course did not, because it's not really something that is relevant in business. So anyways, that's beyond the point, and I digress with that, but oh, not trying to do that. Okay, so let's take a look here, and what we're going to do is one more example, but it's a little bit different. So let's say you were given something along the lines of, let's do this one. Cosecant of 30 equals b over 10. So in this case, they're asking you to solve for the variable, and what is the variable? Well, first of all, let's kind of remember what our rules are here. So cosecant is the inverse of sine. We know that sine is opposite over hypotenuse, so this actually means that this is hypotenuse over opposite. Okay, so keeping that in mind, obviously we can just solve for this algebraically. It would become cosecant of 30 times 10. But if you're not 100% sure of what the cosecant of 30 is, because you can't just plug this into your calculator necessarily unless you've got some next level calculator that I don't know about, but the main calculators that they usually allow on exams and tests won't have that. So we can go ahead and do this. We can say cosecant of 30 is literally 1 over sine of 30. And we know that sine of 30 is 0.5. So this becomes this. Equals b, and then 10 divided by 0.5 is 20, and b equals 20. Okay, you guys? So I'm hoping that makes sense, and I know that some of this might be a review for a few of you if you have already done this part. If it is, please feel free to ask any questions that might pertain to things that you need to know about. And again, I'm going to try not to say pertain too many times today. It's just for some reason in the back of my mind. I don't know why. Like I said, I have not drank enough coffee today, you guys, so forgive me. I clearly need to be more caffeinated. Okay, so obviously when we're going to get questions like this, they're not going to be just easy peasy little things like flip things around and do the algebra, etc., etc. The real reason we learn these identities and all about what they mean is because when we're actually going to be solving trigonometric identities in general, we have to have an understanding of how sine and cosine and all of their reciprocal identities are related. And that's something that obviously takes a little bit more time, but it's okay because we'll figure it out. Now, let me just pull up the right thing that I was going to teach next. Oh, sorry, I had it on the wrong side of the desk. Okay, so what I'm going to teach you guys next are these things called the sum and difference formulas. So hopefully everything we just learned made sense for you guys, and we are going to do some more complex things relating to the stuff we just learned, but I want to make sure we're covering as much as possible in a way that's actually helpful for you guys. So I don't want to review things 500 times if everybody's understanding it. But again, if you don't get something, there's no problem with you asking a question. That's what I'm here for. So let me just write these out for you. Actually, no, I have them here. They're on the side here. Oh, God bless. They're really annoying to write. So if you look over here, this is what we're going to be talking about. So I'm going to erase this stuff here, you guys. I hope that's okay with you. And these videos are most likely going to be posted. Usually YouTube just automatically posts the live, and then depending on how much time I have to make sure that it's all set, we usually just leave them up. So if you want to look at last week's trig unit, trig learning that we did, you can actually go back and watch last week's if you have time and you want to. So we're going to be talking about sum and difference formulas, and this is, again, like I said, this is an MHF 4U, which is the grade 12 course formula sheet, but the reason they have this on here is because this concept that we're going to learn right now actually is something that they involve in the grade 12 course as well. So definitely follow along if you have some time so that we can go over everything properly. So basically what these are for is that if you recall, I told you guys that there are a bunch of standard triangles that we use. We've got the 45, 45, and 90, and then we've got the 90. Wow, it's a terrible depiction of a right angle triangle, but you know what I mean. The 90, 30, 60, and these have their standard things that they are. I forget this one off the top of my head, but basically it has standard side lengths. And the reason that I was saying that we should memorize these is because once you've got these memorized, you can actually pretty much solve basically any question relating to trigonometric identities because you can use the sum and difference formulas. And the sum and difference formulas are just a different way of breaking up the information so that we can solve for something. So let's say, for example, you're being asked, like, for example, you know that 75 degrees is the exact same thing as saying 30 degrees plus 45 degrees, right? Right. But in most cases, you already know what the sine and cosine of 30 and 45 are because you've got those on the unit circle and you've got them in your standard triangles, but you don't necessarily always know a number like 75 what is a perfect identity for that. So let's go ahead and show you how we can use these sum and difference formulas to solve for larger questions like this. So in this particular case, let's say that we're being asked to solve for the sine of 75 degrees. And again, we know that 75 is 30 plus 45. So one way I can break this up is sine of 30 degrees plus 45 degrees. And I'm just going to use a different color here. So here they've called these theta and alpha, as you can see here, theta, alpha. Sometimes they call them alpha, beta. It doesn't really matter. Basically, this is sine thing A plus sine thing B. And I'm just going to use the letters that they're using, the Greek letters, so theta and alpha. And the identity that we're going to be using is this one right here, the sine addition formula. If you can see my little star there. And the identity is originally, I'll put it underneath, sine of theta plus alpha equals sine of theta times the cosine of alpha plus the cosine of theta times the sine of alpha. Okay, so let's see how we're going to make that relate to what we need. So I'm just going to go back to blue here. So what they're really saying is you're basically breaking this down, and the reasons behind this are quite complex, and so we're not going to go into those today. And actually, you really don't need to know the reasons behind it in terms of understanding how this all works, because sometimes when we complicate things too much, it gets to be a little bit K-Razi, as I like to say, and makes us actually get more confused. So here we're going to go ahead and have the sine, because we're saying that 30 is theta, so I'm going to say sine of 30 times the cosine of alpha, which is 45, plus the cosine of theta, which is cosine of 30, times, and you can even, again, this is the proper way to do this, to put these little brackets, but it depends on your teacher. Some teachers are not that picky about that. So sine of 45. Okay, so let's go ahead, and if we recall our standard triangles, there are a couple different ways that you can understand this stuff. I mean, again, if you have a unit circle, you can refer to that, but I'm going to take a look here. So, okay, and again, so in the 90, 45, 45, we have the root 2. Just give me 1 second to make sure these are right. Root 2, 1, 1. And then in the, draw it down here, that's a 90. This is going to be a 30. This is going to be a 60. And I'm just going to double check that I'm doing this correctly because I always flip the numbers on these. Give me 1 second, guys. So we've got so 30 is 1. This is 2, and this is root 3. Okay, good. Sorry, because I always flip those around, and I don't want to give you guys the wrong numbers. I highly recommend writing these triangles down and just having them available to yourself all the time, because it's going to make your life, like I said, so much easier. Truly, like I'm not even exaggerating. If you know these triangles, you don't need to memorize the unit circle, because these are the unit circle. You just literally memorize these two things and you've got the whole unit circle down pat. So keeping that in mind, we know that for sine of 30, we've got 1 over 2, because again, sine of 30 is opposite over hypotenuse, so that's 1 over 2. And the cos of 45 is root 2 over 2. And the cos of 30 is adjacent over hypotenuse. So we've got adjacent over hypotenuse. So that's root 3 over 2. And then last but not least, we've got sine of 45. And the cool thing about cos and sine for 45 is that they're literally the same. Root 2 over 2 again. Okay, so let's go ahead and solve this now. So literally these are just standard multiplications. On this side, we have got root 2 over 4. And then this is plus root 6 over 4. And then we have root 2 plus root 6 over 4. And that's our final answer. So this here, again, and if you're not familiar with radicals, I highly recommend you go back and practice your radicals from grade 10. Some teachers teach them in grade 10, some teachers in grade 11. I don't know what your school is doing in particular, but I will say that I really, really recommend that you understand radicals. Radicals are kind of the basis for understanding how to keep things as fractions, because in math, the most mathematically correct version of things is a fraction and not a decimal, and that's really what we aim to leave as our final answer, is keeping things as a fraction, because I could realistically plug this into my calculator and get some crazy decimal, but it's actually less correct mathematically than leaving it this way with my radicals in place as a fraction. Okay, guys? So we're going to do probably one more example of this type, and we're going to use the tan formula just because that's really where things get crazy. But I hope this makes sense. I, again, implore you to ask questions if you do have questions, because these are concepts that come back over and over again, and there's no problem with me going back and answering questions that you might have, okay? So I'm going to erase this stuff. Hopefully you guys got a chance to write that down. I will say that if you are a student who has, for whatever reason, a need for me to write slower, I actually highly recommend letting me know. You can email us at admin@scholarlyelite.com, or you can actually just go to our website and leave us a message, because I want to make sure that we're accommodating everybody, and for whatever reason if you can't keep up with how quickly I write, then that's fine. We're here to help, okay? So hi there, hi Ramin. What unit is this? This is trigonometry. So this is the first part of trigonometry, not the graphing part. We'll do that later on in other weeks, but this is trig. So hopefully that we can go over this for you guys. Can you please write slower? Yeah, for sure I can write slower. Okay, awesome. Thank you for letting me know. Awesome. Okay, so I will definitely write slower. Sorry about that, guys. I didn't mean to rush through everything. So let me just redraw this triangle here. So we will definitely aim to write slower. Okay, I'm confused. Okay, no problem. So yeah, we'll definitely go over more questions like this, because I know that this is super confusing. Can you elaborate, Ramin, on what you're confused about specifically, and I can go over whatever it is that you have questions about? And then we can definitely do that. So while I'm just waiting for that answer, I'm going to pull up one other thing here. So let's do this here. We're going to use this identity here, the tan one. So we're going to do the tan of 15 degrees. And again, with these identities, I was referred here from my math teacher. I'm supposed to be learning radiant radicals. I already learned about trig. Oh, okay, your math teacher sent you. So basically, Ramin, that's a really good point, and I appreciate that your math teacher sent you. Now, the reason that I'm doing a lesson is basically because we have kids from all over Ontario watching, and so we don't know who's doing what, but we are able to definitely answer any math questions that you have in particular. So if you want to send in your math questions for me to answer, you're more than welcome to, and we can definitely take a break from the lesson. So what I'm going to do is actually put up our website, admin at scholarlyelite.com, not our website, sorry, our email address. And I appreciate Ramin writing this question. So because this is probably something other people were wondering as well. So if you're here from a particular math class and you have math questions that don't relate to the unit that we are doing right now, that's great. You can definitely send them in, and I'll answer those questions in the chat. So if you're, whatever you're confused about, you can send us a question to this email address, and I'm checking that as we go through the chat. Because basically, there's so many different kids watching from all over. We have kids from the GTA, we have kids from Simcoe County, and I know we do have some kids from super north in Ontario as well. So the reason why we're doing trig is just because we've been following our own curriculum. But if you have specific questions about radians and and radicals, you can definitely send those in either through this chat or through through our website, through our email here that I've just written up here. Okay. So Ramin, if you have questions that you want me to answer specifically, I don't have a radians lesson, like a radicals lesson in front of me right now. So I don't want to make anything up off the top of my head, but if you have questions, I can answer them right now in this step-by-step live stream is what I'm trying to say. Goodness. So, and then basically once I get Ramin's questions, we can definitely do some of those as well. So we're probably not, for this in particular, we probably aren't going to cover radicals as a lesson for another week or two, just because we're still finishing up trig. But like I said, we're here to help. So send in those questions that you have about radicals, and I can take a break from what we're doing here to answer those for you, okay? Okay, awesome. So while we're waiting for any questions to be submitted that anyone might have, what we're going to do is, awesome. No, thank you, Ramin. I appreciate all of you guys tuning in. I hope this is helpful for you guys. And one thing I want to note as well is that you guys are probably, even if you're not writing an exam per se this year, and I don't know what's going to happen with this year for you guys, you will be required to know all of this information for next year, and having a really good basis, even if it's just a review, is super awesome as well. Okay, so let's take a look here. We've got, I'm just going to do this one quickly while we're waiting for any new questions that might come in. So if we've got tan of 15, first I want to remember that, again, the whole point of using these sum and difference formula, or formulae, however you want to say that, is basically to just recall that any number is basically just other numbers subtracted. So in this case, we know that, 15 degrees is the same thing as saying 45 degrees minus 30 degrees. So tan of 30 degrees, if we look at this identity right here, if you can see in the identity stuff that I'm looking at over here, we've got tan of theta minus alpha equals tan of theta minus tan of alpha over 1 plus tan of theta times tan of alpha. Okay, so what we're going to do now is basically say to ourselves, and I'm going to erase this little chunk here as best as I can. There we go. What I'm going to say to myself now is basically tan of 45 degrees, which is going to be our theta, minus 30 degrees, which is going to be our alpha. Okay, guys? So there we go. And the way that we're going to write this out now is that tan of 45 minus tan of 30 over 1 plus tan of 45 plus tan of 30. Okay, so hopefully that makes sense for you. And let's go ahead and just plug in the numbers that we know. So we've got tan of 45. Well, we know that 45 degrees here, this triangle here, tan is opposite over adjacent. Well, that's 1 over 1. So tan of 45, this right here, is 1 minus the tan of 30, and the tan of 30 is 1 over root 3. And then basically do our big divider here, and we've got 1 plus tan of 45, which is again 1. And then here we've got, oh, sorry, this isn't a plus here. This is a multiply. This right here. Okay, so we've got times tan of 30, which is again 1 over root 3. Because again, this is 30 degrees. The tan is the opposite over the adjacent, so 1 over root 3. Okay, so we've got that there. So basically, what we need to do now is figure out some common denominators. And the way that we're going to do that is multiply the numerator and the denominator by root 3 on this top part here. So this is going to end up being root 3 minus 1 over root 3. And this bottom part is going to be 1 plus 1 over root 3. And just going to do this here. Oh. Whoa, what is that? There we go. Let me just get back to what I was doing. And then basically, this is going to become root 3 minus 1 over 3, root 3, divided by root 3 plus 1 over root 3. Because basically I skipped a step here, guys, but basically what I did was I did the same thing in the denominator that I did in the numerator, which is multiply the top and the bottom by root 3. And then we know that when we have a division, this actually makes this flipped, and we've got a multiplication. And this is going to end up giving us, actually just give me 1 second to make sure of one thing here. Root 3 divided by 1. Oh, yeah. Sorry, these cancel. That's what I'm trying to say. So those cancel, and again, they cancel because they're exactly the same, and if we were to multiply them together, it's basically like saying root 3 divided by root 3. So now we're left with root 3 minus 1 over root 3 plus 1. Well, I don't know how far you guys have gone into radicals and into math and all of that in this unit so far, but one thing that we want to make sure is that we don't have radicals in our denominators. They really mess things up for us, okay? So I'm going to just pause for a second so you guys can catch up with my writing in case anyone is trying to catch up. I'll give you guys about 10 seconds there to look at everything. Okay. And now what we're going to do is multiply both the top and the bottom by root 3 minus 1. And the reason we're doing this is so that we can rationalize the denominator, or get rid of the rational in the denominator. So let's go ahead and do that. Hopefully you guys have been able to write down what I'm writing here. I'm just going to erase this part. So remember that our last step that we were at is we have root 3 minus 1 times root 3 plus 1. And we're going to now go to our next step, wherein we rationalize that. So we have root 3 minus 1 times root 3 plus 1. And basically what I'm about to do is this. Because whenever we have something like this, we actually take the opposite sign and do that as both the numerator and the denominator of something we're going to multiply. And what this is going to give us overall, or actually I'll give you guys a second to write that down and ask any questions if you have questions about what the heck I'm doing here. So let's go over this like this, okay? Again, think of this as if we're saying x minus y over x plus y times x minus y over x minus y, okay? So let's do the numerator first. X times x, x times negative y, and then negative y times x, and negative y times negative y. Okay, that's what's going to happen here. So first things first, let me get another color. Make this a little bit fancier looking. So root 3 times root 3 is 3, and you can try that on your calculator. And like Ramin was saying, he's doing radicals right now. That is a very common radical concept. So the root of anything times the root of itself is going to be the thing inside of the root. Next we've got root 3 times negative 1, which is negative root 3. Then we've got another negative 1 times root 3, which is another negative root 3. And then negative 1 times negative 1, which, as you can imagine, is plus 1. Okay, let's do the same thing on the bottom, guys. So we've got, again, root 3 times root 3. That's 3. Root 3 times negative 1. Negative root 3. Positive root 3 times, positive 1 times root 3 is now positive root 3. Now this that just happened, this is the whole reason we did this whole thing, because I want to cancel these out. Negative root 3 plus positive root 3 is going to cancel out, right? Because any negative 3 plus 3 is going to cancel out, basically, is what's happening here. Then we're going to do positive 1 times negative 1, which is negative 1. Let's do our collection of like terms. Remember that these kind of radicals, I can now collect, right? So I'm going to say the 3 stays the same on the numerator. This now becomes negative 2 root 3 plus 1. And I got negative 2 root 3 because I'm saying negative root 3 minus root 3, which is 2 root 3s. It's like saying a negative apple minus a negative apple, you've got negative 2 apples. I know that wasn't a great example, but that's kind of the gist of what just happened, okay? So this is the simplified version of what the numerator is. And then basically here, I'm only left with 3 minus 1 because negative root 3 and positive root 3 cancel. And so I have 3 minus 1, which we know is going to be 4. And I'm going to fix that in a second. Just give me 1 second. So we're going to go over here. So now I've got 3 minus... Oh, sorry. We also have 3 plus 1 here. If you look at this, 3 plus 1, which is 4. So let me fix that. So hopefully this is making sense. And I know this is quite complicated. That's why we did an easier version first, because this is kind of insane. But it's definitely important that you guys understand how all of this is working. So please feel free to ask me any question about the minutia of what I'm doing in order for us to kind of get through everything. So now I'm going to add 3 plus 1, which is 4. And then I know I also have minus 2 root 3 because that stayed the same. And then here I've got 2. So as with all math, you know, we love to factor things. We're just factor fiends and we want to do that. So I'm going to factor out 2 in the numerator. So I know that 2 goes into both 4 and 2 root 3, and I can just factor that out. So 2 times 2 minus root 3, which is just 2 minus root 3, and then over 2, and then now these bad boys here, they cancel. Okay? So hopefully that is making sense so far. And now all we're left with, guys, is just 2 minus root 3. That's the answer. Okay, and you can check that on your calculator if you were to literally plug in tan of 15. It's 0.26, and then 2 minus the root of 3 is also 0.26. Okay, so this is just a real fancy way of figuring stuff out. And it does come in handy to understand how to do this, and it also is really important that you guys practice rationalizing the denominator. Because like what I mean is this step that we did here. So basically what happened was we looked at what the denominator was because it has a radical in it. We don't like that. We're not fans of radicals apparently. And so we said, okay, well this denominator is root 3 plus 1. Well, the opposite of that is root 3 minus 1. And the whole point of that is that when we do this FOIL method, we're able to cancel out just like we did here. So I hope that makes sense for you guys. And I know that that's a bit complicated, but it is something that you do need to understand for both grade 11 and grade 12. So it is a good thing to practice and to go over. Hopefully that makes sense for you guys. So I'm going to let that simmer there for like another 5 to 10 seconds so everyone can just write down the steps if you want. And we're going to move on to something a little bit different here. Not too different actually because we don't have that much time, but just something else quickly before we go. And one thing I do want to mention as you guys are writing stuff down is, like I was saying earlier to our friend Ramin here, if you have questions from your class that you're not sure about, we're here to help you. The whole point of this is for people to be able to submit questions and get the help that they need. I know that the YouTube chat is not really conducive to you guys submitting more complex questions like this one, for example, or like radical questions, which is why we've opened up our email. This is admin@scholarlyelite.com. We're originally an in-home tutoring company here in Barrie, but we operate all throughout Ontario, and we also offer online tutoring, and we've offered it for many years now. So this is not our first rodeo, and so if you do need help on a more one-on-one basis, you can get in touch with us. But if the whole reason that we are doing this right now is because we know that people's parents might have lost their jobs. You might have, you might be going through financial tough times right now, and not everybody is, but I know a lot of people are. So that's why we've opened up freemathhelp.ca, because we know during this time not everyone can, afford to have extra help. And so that's why we're here every week, and you can submit questions to us throughout the week that we can answer during the live stream. So for example, if you have questions about radicals, even if we're not doing radicals in the lesson that week, we can answer them. Just submit them to our email address. Okay, guys? We're here to help, and if you do need anything like that we can answer during the live stream, we're happy to do that. Okay? So before we go, what I wanted to do was just kind of one last thing, if I can find the thing I was looking at earlier. You know what, before we go, I'm just going to kind of go over the Pythagorean identity. That's this one here. And I'm going to talk about why it's important. And if you guys have any questions, you're welcome to submit them before we wrap up everything, because we're going to do the grade 12 class next. So I'm just going to start erasing this here, guys. Hope that's okay. And yeah, I really appreciate your teachers sharing this. I know that for the schools, they don't have the capacity to do this for every single class, just because takes a lot of technology to be able to live stream like this. Not a lot, but more than the schools can afford right now. And that's really awesome that your teacher was able to share this link with you guys. Okay, so let's just quickly discuss the Pythagorean identities, and then hopefully next week we'll go over that again a little bit more in depth. We're going to talk about some tricks I have for solving identities, because I actually have some step-by-step ways that you can always step-by-step tricks that you can always apply every time you're solving an identity, instead of trying to kind of maneuver everything from scratch. So here you can see these Pythagorean identities. We've got sine squared of theta plus cos squared of theta equals 1. And these other ones, but we're not going to talk about these right now. We're just going to deal with this particular identity. This is a really important identity to know and understand. I'm going to rewrite it because it looks a little cray-cray. Let's fix that right quick. So sine squared theta plus cos squared theta equals 1. Okay, so this is a super important identity because when we start solving trig identities, it's really important to understand how we can manipulate this. So just algebraically and logically, we can manipulate this very easily by moving certain pieces of it over to the other side of the equation. So if I wanted to isolate sine squared of theta, I could actually just move cos squared theta over to the other side by subtracting it. Because it's positive on this side, the opposite operation would be the subtraction. Cool. So we got that. We can also isolate cos squared of theta by doing the exact same thing, by just moving sine squared of theta over to the other side of this. Okay? Alrighty guys, so this is super important because sometimes you'll see in an identity, and we're going to learn about identities more next week, but sometimes you'll see in an identity that you have, for example, cos squared of theta. And instead of saying cos squared of theta, it would actually be helpful to your identity to substitute 1 minus sine squared of theta into that identity. Okay, so this is how we manipulate this. These are really important to understand and to know, and we will touch on those again hopefully next week. And then also the quotient identity that I want to show you guys is this one here. So we've got tan of theta. So tan of theta, which we know is opposite over adjacent. Another way of saying tan of theta is saying sine of theta divided by cosine of theta. And if we know that we have our CAS rule, right? In our CAS rule, I think it's like this. So in our CAS rule, we know that here cosine, sine, and tan are all positive. Here we know that tan is positive. The reason that here and here tan is positive is because here we've got positive x, which is cosine, and we've got positive y, which is sine. And if you are confused by that, go back and watch last week's grade 11 class. We did talk about that a little bit. And the week before, although we don't have that one recorded, unfortunately. But if you do have questions, again, we're going to go into stuff like this a little bit more in depth. And the reason that we are doing trigonometry more in depth is because this unit is the one that truly carries over into grade 12. And so even though it is just one unit for grade 11, technically 2 with the graphing one as well, it's super important for the next year's stuff, okay? So basically we've got tan of theta, and it's super important to remember that it's sine over cos. And one way I remember that is that it's not alphabetical, it's the opposite way around. The sine is on the top and the cos is on the bottom. And then the cotangent of theta, like we were learning earlier today, is this flipped. Okay, guys? So anyways, we don't really have time to get into anything else. So I'm going to let you guys go for today. I hope that this was helpful for you guys. Thank you, Flochi, for your message. I appreciate you guys joining. I think it's awesome that you guys are really dedicating yourselves to understanding things while school is closed. And even though, obviously you guys have assignments and stuff, it's something where you are taking time out of your day to learn even more. So I hope you have an awesome day, and we're going to transition over to the grade 12s in about 1 minute. So hope to see you guys all again next week. And again, if you need to submit questions, send them to admin@scholarlyelite.com, and our team at Scholarly Elite Tutoring will be able to bring questions forward to next week so that we can answer them during the live chat. And if you do need one-on-one tutoring, we are also offering online tutoring. You can go through our website and do that there, but whichever works better for you guys, okay? Have an awesome week, and stay safe and healthy, and we'll talk to you guys again next Thursday, okay? Same time, same place. We'll see you soon. Bye. Actually, we'll just leave that. Okay. Alrighty. So I want to welcome any grade 12s who are joining us right now, and thank you for joining us at freemathhelp.ca. We are here today for you. We are here to help you with math and get as much knowledge to you as possible. The way that this works is that basically every week I have prepared a lesson, but you don't have to only ask questions about the lesson. If you have questions from your class, send them in and I will do my best to answer them as best as I can. Because realistically, that's what we're here for, is to get you guys the help when you need it. So if you do have questions, what I was telling the last group of kids was that you can email us at admin@scholarlyelite.com. Make that bigger. So then that way I know that for the grade 12 questions, like they're not really things that you can necessarily just shoot into the chat, because obviously some of them are a little bit more complicated. So that's why I'm saying you can send them in the to our email, okay? So that's our email there, admin@scholarlyelite.com, and you can send questions there even during the live stream, but you can also send them during the week, because obviously you might not be working on something right this second, but if you do stumble upon a question that you have, you know, that you want us to focus on a little bit during next week's live stream, you're more than welcome to send it in. Okay, guys? The whole reason that we're here is to help you guys. You know, this is something where obviously we have kids from all over Ontario watching, and you guys aren't necessarily all doing the same unit at the same time, which is why we're kind of following our own little mini curriculum here that's based on the real curriculum. But again, if you have questions, there's no problem with you sending them in, either through the YouTube chat right now or to our email, which is admin@scholarlyelite.com. Okay, guys? So I'm just going to quickly grab my grade 12, materials here. And we can go ahead and do that. And hopefully everyone can hear me properly. If you can't hear me, that's just feel free to shoot a message in the chat there, and so I can yell, I guess, a little bit more. So yeah, so what we were just talking about in the grade 11 class actually really flows well into what we're going to talk about today for the grade 12s, because this thing right here that I'm twisting around, this is the, you know, the holy grail of identity formulas. And this is actually the MHF4U formula sheet for kind of overall, because these are really the only formulas that the curriculum allows us to give you guys on exams and stuff. But yeah, so these are all really important formulas. And what I wanted to touch on today, because I actually had someone let me know that they are struggling with double angle formulas and how those all work, is the double angle formulas. And last week we talked a little bit about trig tips. Wow, sorry guys. Clearly I've been talking for like 6 hours straight today, so just forgive me and my inability to say words properly. But today what we're going to talk about are these bad boys right here, double angle formulas. We're going to start with that, and then we're going to do some other stuff as well. Let's see, I want to change my color on the pen here. Oh, I wish they had more colors. Oh, they do! Oh my god, this is so exciting, you guys. We're all figuring this out together. So let's use this. This is kind of fancy. I like that. Okay, so using my new fancy color that I just learned I can use, we're going to circle this here. This is what we're going to be talking about quickly. I'm going to do an example using a double angle formula. So last week, the chat got cut short because my internet was kind of a hot mess, so hopefully that doesn't happen this week. And it'll be all fine and dandy. So as you can see here, and hopefully this is large enough for you guys to actually see, but this identity right here, this sine 2 theta equals 2 sine of theta times cos of theta. That's kind of what we're going to be talking about today. And the question here that I got submitted was, oof, goodness, my writing skills. Let's do that again. The question I had submitted was this: sine 3 theta equals -4 sine cubed theta plus 3 sine. And at first glance, you look at this and you're like, oh my God, what the heck is this? Why? Like, what, like, you know that thing that's like, hi, Jasmine, and it's like, well, why'd you do this? Why? That's how I feel about some of these trig questions, you know? That was a very bad rendition, but I think you guys know what I'm talking about, that TikTok thing, where it's like, hi, Jasmine. Anyways, I'm not going to be weird. We're just going to learn this. So basically, this is an identity. Your teacher or someone's teacher has asked them to show them why the left side, or the left side, LS, my bad, is equal to the right side. That's really the basis of identities, is saying like, why the heck does the left side equal the right side? And then you have to do a bunch of crazy math to prove that you're a math genius and you can figure it out. So today's trick that I'm going to teach you guys for identities is really just about how to break them down in a way that's a little bit more palatable and a little bit easier to understand, because I know that when we look at these, we're like, what the heck? Why would someone do this? So in the same way that I was just teaching the grade 11s, you know, it's an example like 15 is the same thing as saying 45 minus 30, right? There's two different ways of describing things, you know? It's like saying little brother and then also saying annoying person. They're the same thing, you know? So another way that we can say this is by doing this. Sine of 30, not 30, sorry, sine of 3 theta is the same thing as saying sine of 2 theta plus theta, because 2 theta plus theta is 3 theta, right? And keeping this in mind, we can recall our sum and difference formulas, these boys right here, and in particular, we're going to be looking at this one right there. And we can break this down even further. I know, and you're like, why would I want to do that? Exactly. That's a great question, but not the question we're going to answer right this second, because we need to do the math, you guys. Okay? So when we're breaking this down, obviously we're going to follow the same rules that are right here. And what I want us to be very aware of is making sure that we're labeling these. So here on this particular formula sheet, they're using theta and alpha, so we're just going to use that, although I find that a little bit confusing when we have thetas already. So just keep in mind, you can call this alpha and beta. It doesn't matter as long as you follow these exact, like if you put the placement in the same spots, okay? So we got that. All right, well, how can we apply this in a way that makes sense? Well, very easily, we can take a look at our original addition formula here, the sine theta plus alpha, and we see that sine theta plus alpha can be denoted as sine of theta times cos of alpha plus cos of theta times sine of alpha. Okay, girl, we can figure it out. It's not too crazy. So we've got sine, and I'm going to write the original thing here. So sine theta cos alpha plus cos theta times sine alpha. Okay, so let's go ahead. We know that theta is 2 theta. Like, that's what we're calling it. So here we're going to plug that in, sine of 2 theta. And then we know alpha is theta. I know I don't mean to confuse you guys, but it's just I'm trying to follow this identity worksheet that we've, not worksheet, this identity, I don't know, list that we've got here, so I don't want to mess you guys up too much. So cos of alpha, well, that's just cos of theta. And then here, cos of theta, in this case, we've denoted theta as 2 theta, so we're going to put cos of 2 theta times sine of theta. If anyone is confused by that, feel free to leave a comment. I'm happy to answer what the heck just happened here. You know, another way that you can say this is, you know, call this A and B, or call this, you know, pinky in the brain. It doesn't really matter what you call these things. As long as you're following these exact breakdowns in the exact order that are in the formula, you can call this whatever the heck you want, okay? So let's go ahead and take a look at our next step. And I'm going to show you guys the trick that I use when solving these kind of questions, okay? So in this step, we've got sine 2 theta times cos of alpha. And what we do know is that we can break this down further using our double angle formula right here. So we know that sine of 2 theta is equal to, right here, 2 sine theta times cos of theta, okay? And I don't know what devil created all of this for us to do, but it's part of the curriculum. I did not make this up, you guys. So don't blame me, I'm just the messenger, okay? So we're gonna take this here, sine of 2 theta, and using this double angle formula, we're gonna break it down. So let's go ahead and do that. We've got 2 sine theta times cos of theta. Oh, let me put a theta there. Times cos of theta. Plus. So let's take a look on this side. What do we have over here? Well, we've got cos 2 theta. And if we look back over here at our double angle formulas, we've got a crazy way of expressing that as well. So the way that we can express that is cos squared theta minus sine squared theta. And that's exactly what we're going to do. I want you guys to know that when you have identities, most of the time, if you feel like you're stuck, there's almost always another way you can break it down. And don't let yourself get down if you're not getting these questions the first try. Even those of us who have been tutoring and teaching math for years, if we're given a new question like this, it does sometimes take us 1 or 2 tries to get the right answer, because you can't always assume what's going to happen 5 steps down until you get there. So again, just don't, I'm just kind of trying to say basically, don't let anything get you down in math. You're probably a lot better at math than you think you are, and it just sometimes is about trial and error. Okay, so I hope this makes sense. This is what this is, because using the double angle formula, and this is this using the double angle formula. Okay, so anytime you get a question like this, and this is a very common grade 12 question for the MHF4U class, this is basically what they're asking you to do. Keep on breaking it down. Just go as much as you can. Okay, so now I'm going to teach you guys my trick, because this is what I have found. The reason I created this trick is because over the years, I found that what people found most confusing was not the sine and cosine piece of it, but was actually whether or not they were allowed to do certain things, because adding letters makes things confusing. So let's see what we got here. Sorry, I'm just trying to pick a fancy color, because this is what brings me joy in my life, you guys, okay? So let me have this one thing. So, okay, let's go ahead and do this. Now, what we're going to be remembering are the following, or is the following. I'm going to say sine of theta is x, and cos of theta is y. I don't actually mean this necessarily. What I'm just doing is giving each thing a different name so that I can show you guys what to do to make this a little bit easier. So here I've got 2 sine of theta. I'm going to write that down as 2x. Here I've got a cos. That's now a y. Here I've got another cos. That's now a y. Plus, here I've got cos squared. That's going to be, actually, you know what? I'm going to do one more step before we do this. Hold up. Let's fix this real quick. I'm actually going to change this to make it a little bit better. So this is now going to be 2 sine of theta cos of theta times cos of theta plus, so here, right here, I'm going to take this cos squared of theta, and using the Pythagorean identity and by rearranging it algebraically, I'm going to change this into 1 minus sine squared theta minus sine squared theta, which is basically the same thing as saying 1 minus 2 sine squared theta. So I'm going to show you guys that in a second. Sine squared theta. I'm also trying not to write too fast because in the grade 11 class, people were telling me that I was writing a little too fast. So if I am and you want me to slow down, just yell at me in the chat. That's fine. It's no problem. I can handle it. Okay, cool. All right, guys. So again, if you're confused by any of these steps, just let me know. That's not a problem. We can go over stuff. Honestly, this is a tough unit and I want to make sure you guys understand everything, okay? Okay, so let's take a look here at how to actually make this way easier than it actually is. Okay, so let's use this color. So again, keep this in mind that I'm calling sine of theta x and cos of theta y. And this is not a step that you necessarily need to show on your tests. This is just my method that I've used over years of tutoring to help kids understand what they are and aren't allowed to do within these identities. Because a lot of people who are really good at math find trig identities so difficult. And I get it. It's because they look insane and they are so complex, when in actuality, we can just break them down and make them really easy to look at. Okay. So I'm going to basically start using that information. So here this is going to be 2x because sine is x. And then there's a y. And then times y because cos is y, as we know from here. Okay. And then plus 1 minus 2x squared. And then times x. Okay. So as you can see, if we know how to do basic algebraic functions and normal math, we can figure this out. So this is now going to become basically just as we know from multiplication rules. This is 2xy squared plus, when I multiply this in, right, this into here and then this into here, this is going to become plus x, like that kind of x, minus 2x cubed. Okay? So, again, this is not like a requirement of doing this type of thing. This is just me teaching you guys a strategy that I've used with many of my students over the years to get people to understand how much easier these things are than they look. Because like I said, they look insane, but they're not actually as crazy as they look. Okay, guys? So now that I know that this is what this is supposed to look like, I can actually just go ahead and go back to my blue and go back to my original question, and I'm going to write it like this. 2 times sine of theta, because again, x, 2, times cos squared of theta, plus sine of theta, because of that, minus 2 times sine cubed, right there, guys, because of that and because of that. Okay, I hope that makes a little bit of sense for you guys. We're going to keep going. We're going to keep on trucking. So I'm going to move this up, which is going to get rid of this a little bit. Oh, I hate that this moves everything. I wish that it didn't. Anyways, let's just do that to make some more space here. Okay, you guys. So keep on trucking. We can do this. Now, again, it's important to remember that understanding these identities is really going to help you when you have crazy questions like this, because if you don't understand when and how to apply them, it makes it really difficult. So I highly recommend, as I was saying to the grade 11 class, if I just pull this down for a second, highly recommend fully memorizing the Pythagorean identity, the first one that you see here with the star next to it, the sine squared theta plus cos squared theta equals 1. That's like the #1 jam. You definitely need to know that one, otherwise your life is going to be much more difficult. The rest of these, your teachers will probably give them to you, and so you don't super need to memorize them, although I know some schools in Simcoe County make their kids memorize them, which is not nice in my opinion, but no one asked me. So let's keep going here. We're at this point now, and we need to break this down further. Well, let's make our lives easier yet again and start applying some simple factoring and stuff like that. Now, okay, my first main trigonometry tip for you is try to get things when you see that like most of this formula or most of this equation is in sine, like obviously here we have sine of theta, here we have sine of theta, here we have 2 sine cubed. obviously something's up here, and it would just be easier to make everything in terms of sine. So let's do that, because we know that through the Pythagorean identity, cos squared of theta can be rewritten as 1 minus sine squared theta. So why don't we go ahead and do that? So this is going to be 2 sine theta, because that stays the same. This guy stays the same. This guy stays the same. This guy is going to become 1 minus sine squared theta, because we feel like it, and it makes life easier. Plus sine of theta minus 2 sine cubed theta. Okay, guys. So hopefully that's making sense so far. Now, moving on to continue this making a little bit easier. What I'm going to do, pull up my red here again, and now put this into terms of y, or x, sorry, sine is x. So we've got 2x minus 1 minus x squared plus x minus 2x cubed. So again, these are not as daunting as they look, because we can always just break them down in terms of x's and y's, and it makes life so much better. Okay? Now, let's go on to our next step here. Actually, I still need the red. My bad, my bad. And we're just going to simplify this. So we're going to multiply this guy in here. So we get 2x minus 2x cubed plus x minus 2x cubed. So hopefully that makes sense, you guys. Again, if you're confused by any of this, just shoot me a question. No big deal. I'm happy to answer it. Okay, so again, we can actually simplify this a little bit more, because there are like terms in there. It just depends on what you want to do in this particular case. So here, again, just to keep things in context, we can rewrite this as 2 sine of theta minus 2 sine cubed theta. And remember that cubed has to go in here, and then plus sine of theta minus 2 sine cubed of theta. Okay, guys. So now we can actually simplify this, and it's so much easier to simplify it first using our x's and y's, because that's just what we're used to doing, obviously, right? So here we've got 2x and x, so that's going to come together to make positive 3x. And here we've got negative 2x cubed and negative 2x cubed, and that's going to come together as negative 4x cubed. Okay? So hopefully that's making sense for y'all. But again, this is a strategy that I use all the time when solving these types of questions, because when you break it down in terms of x's and y's, your brain just automatically knows what to do. When you add all these other nuts and crazy letters, your brain looks at it and is like, nah, girl, not doing that. That's ridiculous. And it kind of just shuts down, right? I mean, if you're like a trigonometric identity genius or savant, more power to you. But I know that I remember being in grade 12 and being really being really afraid of getting these kind of questions, because I just didn't understand what was allowed and what wasn't allowed. And as soon as it clicked that, you know, this is just normal factoring, it's normal, you know, addition of like terms, all of that, that's when it kind of made my life so much easier. So now to get to the final answer, finally, after all my blabbing, guys, jeez, is negative 4 sine cubed plus, sorry guys, that was just like a bunch of papers that fell off of my desk. Give me 1 second. Probably going to collect those. Okay. This is our final answer. And if we recall, that's what they asked us to look for in the beginning. Okay? So all of this work was just to get this very simplified answer. And that's really what these are 90% of the time, is just simplification. So again, this is a strategy I highly recommend. Sorry, let me pick up those papers that fell before I lose all track of where they went. There we go. Okay, so again, these are not as crazy as they look. My number one tip is using this XY method. It's really a lot easier than trying to isolate things when you have all these letters. And also just really remembering that most of the time with trig identities, the number one thing that you can do is put everything in terms of one thing. So either sine or cos, and make everything in terms of sine or cos if you can, because that helps you usually cancel stuff out. It helps you bring like terms together, and it just makes things overall easier in general. Okay, guys? So that's this nuts question. I'm going to leave this like this just for like 20 seconds so that whoever might be following along can continue copying it. And while you guys are copying, we're going to look, I'm going to just open up the next thing we're going to look at. Okay, you guys, so we're going to do another trig identity, and then we're going to basically probably wrap it up at that point and be done. Okay, so I'm just going to start another page here, pull up our identity sheet, expand, so fancy. Okay, there we go. Alrighty guys, so let's take a look at another identity. This one's a little bit easier, but the reason I started with the double angle formula one was really because it illustrates my point so well. And who doesn't want that, obviously, to sound super cool, right? So let's take a look here at this one. Am I looking at the right thing here? So if your teacher really loves you guys, and clearly they do, they're going to give you maybe something that looks like this. And I know that some teachers use theta and some teachers use x. They're the same thing. It's an unknown variable. Theta is the more correct one technically because of life. I'm kidding. Because of the fact that theta literally means angle. But you can use x as well. And I actually used to be much more well versed in using x, and now I just use theta most of the time. Okay. Alrighty guys, that's a plus, not a cross. Good lord. What am I trying to do here? Okay, you guys, so let's take a look at this. My first tip for when you get questions like this is to look at which side looks more complicated. And obviously, anytime we have tan involved, tan is our really complex guy. He makes things very annoying. So it's important that we kind of address that side first. So we're going to be looking at this right side of the equation today to make things a little bit easier. So on the right-hand side, we've got tan squared x, or tan squared of theta, minus 1 over tan squared of theta plus 1. And obviously, we know that based on this quotient identity, tan of theta is sine of theta over cos of theta. So this is going to be a real messed up looking equation, but we can do it, you guys. I believe in us, so we're going to be just fine. Let's take a look here. Now, one thing I did want to address, actually the last question, but I thought, you know what, we'll do it for this one because it's a little bit, it makes more sense. Another thing that I was really confused about in high school, I literally specifically remember being confused about this, was if you had like tan squared of theta, and it means obviously it looks like this, well, that's the same thing as saying tan of theta squared, like this. Or same thing like this, sine squared theta, it's the same thing as saying sine of theta times sine of theta, right? It's nothing crazy. It's not fancier or anything different. The same rules of exponents apply every time. Okay, guys? So just wanted to address that quickly. Alrighty, guys. So let's go ahead and do this. That's an equal sign. I'm just bad at drawing. You guys get it. Looks like chicken feet. That's okay. So sine squared theta over cos squared theta for the top part. So let's do the numerator. We've got sine squared theta over cos squared theta minus 1 over sine squared theta over cos squared theta plus 1. Okay, simple enough, right? And again, remember that tan theta is sine theta over cos theta, so it would make sense that when we square it, which I'm going to show you guys here, when we square tan of theta, that means that we've actually squared this formula. And if you remember our power rule, go and do that, and we get sine squared theta over cos squared theta. So that's what's happening over here. I just wanted to elaborate on that because I know that some people find that confusing. Okay, you guys, so let's break this down as best as we can. Now, in our next step, we're going to make common denominators. And that's another tip I have for you guys. Most of the time, the way to solve these is by creating a common denominator. It's going to make your life, again, so much easier. I don't know how many times I can say that today. So sine squared of theta, we're just dealing with the numerator right now. I'm going to do that so you guys can see what I'm talking about. So let's deal with the numerator. Here I've got -1. I can make that into a common denominator by multiplying the numerator and the denominator by cos squared theta, right? Now, obviously we know that 1 or -1 is the same thing as saying -1 over 1, which makes it a fraction. So let's go ahead and use that knowledge over here in a way that is efficient. So here this is going to become cos squared of theta, cos squared theta. Okay, you guys? And we're going to do the same thing here. Let's erase some of this garbaggio that I drew. So I'm going to get rid of that 1, and instead of writing the number 1, it's going to be cos squared of theta over cos squared of theta. Well, some interesting stuff is going to happen now, because now that we have a common denominator, we've got sine squared theta minus cos squared of theta all over cos squared theta. And if you're confused by that, it's just simple fraction stuff, you guys. It's nothing fancy. Just because we have a lot of letters in there doesn't mean that it's anything different than what we've been doing all these years of math, okay? So on the bottom here in the denominator, we've got sine squared theta plus cos squared theta over cos squared theta. So again, when I'm teaching these, I'm not showing these to you guys so that you can perfectly write stuff down. You can, and I highly recommend writing stuff down. What I really want you guys to gather from this hour is more the general approach that I am using and the tricks that I'm using. And I use the word tricks like loosely. I mean the strategies that I'm using. So again, like in the last question, we did the XY strategy. We always want to make things in terms of one particular identity. So whether it's sine or cos or whatever. And then also my trick here, and that's something that you guys do want to keep in mind, or that you should keep in mind, is using common denominators. That's really what it's all about in this game that we call life, aka trig identities. Okay, so okay, we're here now. We've got, this is our numerator, this is our denominator. Cool. So up next, we're going to get to a point where we probably should start dividing stuff. So I'm just going to move this up so we have some space. And what we're going to do here is actually just write this out like this. So I'm going to write the numerator first, sine squared of theta minus cos squared of theta over cos squared theta divided by sine squared theta plus cos squared theta over cos squared theta. And as we know, when we have a fraction division, it actually becomes a multiplication through magic. It's not really magic. It's like a complex algorithm, but we don't care about that. We just care about the fact that it happens. So we're going to multiply and flip the second fraction. So now we're going to get cos squared theta over sine squared theta plus cos squared theta. And again, remember, simple math rules still apply here. And what's really happening here is that we gonna cancel these bad boys out. Cos squared theta divided by cos squared theta is 1, you guys. And that's all that's happening there. So now what we're left with in this situation is sine squared of theta minus cos squared of theta over sine squared of theta plus cos squared theta. So I'm going to give you guys a second to write that down and catch up. And if you have any questions, feel free to submit them. We're going to go to the next step in a second here. Okay, you guys. So this is where the magic truly happens. Remember our Pythagorean identity that I told you, like, he's your number one jam. It's all you should ever care about. Like, literally everything in math. Not everything in math, but like a lot of trig just boils down to this guy. So we've got sine squared theta plus cos squared theta equals 1. This guy right here, our number one friend. Well, that's going to come in handy because like your brain, as soon as it sees this denominator, should automatically be like, ding, 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 that should be 1. So that's what we're going to do. That is 1 because sine squared theta plus cos squared theta is 1. So I'm going to change that and make my life so much easier. Cool. Well, let's keep going here. Now that I know this is 1, I know that my numerator can just be written like that. I don't need to have a denominator anymore because 1's like that guy on the team that like no one gives credit to, but he's there all the time, you know? So we can get rid of him for now. He's a nice guy, but we don't need him around. So that's what we've got here. And now I am needing to recall what was the original question. Well, the original question is that they want us to show that these two identities are equal, and we're not there yet. So we have to keep going. We must carry on, you guys, okay? So remember, again, using this same identity, the Pythagorean identity of sine squared theta plus cos squared theta equals 1, we can actually solve a lot of questions by converting whichever one is more important to us. And we know that our original question wants us to be in terms of cos, so I'm going to change this part here. And I'm going to change that to, like, again, I'm going to show you guys the identity over here. Sine squared theta plus cos squared theta equals 1. And if I was to rearrange that, it would be 1 minus cos squared theta equals sine squared theta. Well, I'm taking this sine squared theta and using that identity here. 1 minus cos squared theta minus cos squared theta. Okay, you guys. So as we know, again, using that rule I was teaching you earlier, this is basically like saying 1 minus x squared minus x squared. Well, we know that that equals 1 minus 2x squared. And that gives us our beautiful answer here in sunny California. I'm just kidding. It's snowing outside. We're in Ontario, but that's okay. We can handle it. 2 cos squared theta. And that, my friends, is our final answer. Took a long time to get there, and it took a lot of ridiculous math to get there, but it's not as hard as the question would make you think it is when you take it at first glance. So remember, and we're just going to kind of go through this quickly, but I'm going to draw down here so that people can write down what I just wrote. Give you guys about 10 seconds to do that, and then I'm also going to drink some water so that I don't dehydrate myself, and we're going to explain all the steps quickly before we move on to the next thing. Okay, so again, hopefully this has been helpful to you guys so far. And if you have questions about this or any other questions pertaining to the MHF4U, aka Grade 12 Advanced Functions curriculum, and even calculus, like if you're in calculus right now and you're sticking around, you're a trooper and you're more than welcome to send us calculus questions as well. I actually like calculus better than advanced functions. I think it's an easier course. Not to say that all of it is easy. So if you guys have questions, feel free to send them in. But basically the gist of what I'm trying to say is you're welcome to send in questions. You don't have to send them in just through the chat. You can also email them to us. I'm going to pull this up here so you can see our email address. Oh, I didn't even write it on this one. I will write our email address for you guys. So you can email us at Scholarly Elite Tutoring. If you have questions that are not related to the stuff I'm working on right now, that you want us to answer, because that's really why we're here, guys, is to get you guys the help that you might need when you need it, okay? And then basically any questions that are submitted during the week, we just answer during the next live stream. So we'll answer them next week, same time, same place, okay? So you guys, let's keep on trekking over here, alrighty? So up until now, we've been working on identities, and I'm debating maybe doing one more identity at the end. But for right now, we're going to take a pause on identities because I also wanted to cover one other thing for you guys, which is equivalent expressions using related angles, because that's also super important. So let me just pull up the thingamabob here. So if we take a look at this formula sheet that I'm just putting here, we can see that we've got our equivalent trigonometric expressions right here. Okay? So basically, like with all trig stuff, whoever created this situation and whatever nerd sat and figured this all out, they're the worst and they like making our lives hard. But it's okay because the whole point of us doing this today is to take all this crazy stuff that these nerds put together and make it easier for you guys, okay? So, God bless, that's what we're gonna do. And we're gonna talk about how we can apply this equivalent trigonometric formula information to the stuff that we know. Now, one thing I also wanna say is that this sheet here doesn't necessarily have half-angle identities, but they are usually quite important for solving stuff as well, okay? Now, one thing I want to discuss quickly about how this all works and why equivalent trigonometric expressions even make sense. It's just doing a quick overview. Sorry guys, let me fix that. Doing a quick, oh goodness. Doing a quick overview is what I'm trying to say of the unit circle. So when we talk about the unit circle, if you remember from grade 11, in degrees we have 0, 90, 180, 270, and 360 if we go all the way around. Now, let me draw kind of a circle. Guys, pretend this is a good circle, okay? Just do me that favor, do me that honor, and just pretend like I can draw. So, got this. So now that we know those in degrees, by grade 12 we expect kids to know radians. So here we've got 0, and we've got pi by 2, which is the same as 90. Here we have pi. Here we have 3 pi by 2. I'm pretty sure. Let me just double check. Let me look at my unit circle just to make sure I'm not telling you guys crazy stuff that's not even real. There we go. Yep, it's 3 pi by 2. Sorry guys, just wanted to double check that. And then this is 2 pi for 360, okay? So when we have a unit circle, we know that obviously we have angles, like for example, the angle 30 degrees is the same thing as saying, like this, let's say that this is 30 degrees. Here, it has the same terminal arm as 360 degrees, right? Now, keeping that information in mind, that's where all of this equivalent trigonometric expression related angle formulas, that's kind of the basis for them, because we know that just because something is not the exact same number, it doesn't mean that it doesn't have the same properties of sine and cosine. And that's where that comes into play, okay? So just taking a look here. And again, as we're wrapping up this lesson, if you guys have questions of your own that don't have to do with trig, feel free to send them in now so that we can get those covered, okay? So kind of the purpose behind these is to really examine is to really examine how we can use them in a way that's helpful to us. So say we were asked tan tan of 7 pi over 8. Okay? And we know that 7 pi over 8 is another way of describing just an angle. So what we want to do is take a look at this, where is it? This identity, which is tan pi plus 0 equals tan of, not 0, sorry, tan of theta, my bad, equals tan of theta. And so in this case, what I'm going to do is I'm going to say, well, tan of theta, which is 7 pi over 8, is equal to tan of pi plus x. And the way I can break that down is actually making pi into 8 pi over 8 plus x. Okay? And then basically what I'm going to do here, and this is kind of a backwards way of doing it, but it's a strategy, so I want to show you guys this. Tan pi over 8. Another way we can say that is negative pi by 8. Okay? So hopefully that makes sense for you guys. And this can kind of just become that sort of thing. So this right here is another way of expressing this. And it's something that we can use. And we're not going to go too deeply into this because we don't have time to do this whole thing and also the other stuff that we wanted to do. But that's just to give you guys an example of how we do questions like that. So if you're given a question like, for example, cos of 9 pi over 4, you can solve it. So let's go ahead and try that one. So say you've been given, this unit circle, and you've been asked, oh my gosh, I hate when this does this. There we go. You've been asked to solve or express cos of 9 pi over 4. And hopefully this is making sense for you guys. So we know that cos, based on SOHCAHTOA, good old SOHCAHTOA, is adjacent over hypotenuse. Right? And what we're going to do here is use some solving tricks to make this make sense. Okay, you guys? So first of all, I can see that if I was to do this whole unit circle in terms of the fraction with a denominator of 4, that's actually not too crazy to do. If I know that my normal unit circle is 0, and then pi by 2, and then pi, and then 3 pi by 2, well, if I just want to change the denominator to 4, I can really easily do that. Sorry, this is 2 pi. Right? So what we're going to do is change this to 2 pi over 4. We're going to change this to 4 pi over 4 because 4 pi over 4 is the same thing as saying pi. And then 3 pi over 2, we're going to again multiply by 2 to get 6 pi over 4. So hopefully that's making sense for you guys. Very cool. And then what we're going to do is basically use some of the information that we already know. So we know that pi by 4 is another way of saying 45 degrees. And if you remember our standard triangles, and it depends on what teacher you had. Some teachers don't teach these. We've got root 2, 1, 1. This here, this guy right here, is something I highly recommend you memorize. But because you're in grade 12, I'm going to recommend that you memorize the Radians version of it, which is pi by 4, 90, or pi by 2. It's the same thing. The ratio is the same. It's just you're using radians, okay? Alrighty guys, so keeping that in mind, and if we know that we've got our unit circle, our standard rules, oh, let me fix that. Oh, I hate when it doesn't start at 0, 0. Okay, that's about not what I was trying to do. Let's use this. Okay, one last try. Ooh, we killed it. Perfect. We got it. So just as like we did in grade 11, you're basically going to use this to your advantage and know that this part here, from 0 to here, it's pi by 4. Okay? Pi by 4. There we go. And we know that because this is the unit circle, we can use our little rules to figure stuff out. So this here, it's just another version of this. So this is going to be 1, this is going to be 1, and this is going to be pi by 2. Okay, so now, also I should put my x's and y's here. Goodness. And what we do know is that 9 pi by 4 is another way of basically saying 8 pi by 4 plus pi by 4. And 8 pi by 4 is like saying 2 pi, right? So that means that this went all the way 360 degrees, 2 pi, and then it continued another pi by 4, right? So this is an angle that's basically going to have the exact same properties as pi by 4. It's in the exact same quadrant. It's in the exact same position. The terminal arm is not any different in any way. And so we can use that information to our advantage. And if we know what pi by 4 is, then we also, if we know the cos of pi by 4, then we also know this because of that information. Okay, guys? So basically, I know that the cos of pi by 4, which is, let's look at this, adjacent, my bad, adjacent over hypotenuse, which is 1 over root 2. And I know that we're not fans of radicals in our denominators, so we want to rationalize that denominator, and we're going to get root 2 over 2, and that's our answer for this question. Okay, I'm going to let that simmer for a second. You guys can write that down, and we'll do another example if we have some time. Okay, so you guys go ahead, write that down there. I'll give you about 5-10 seconds to ask any questions if you have any about all the stuff that I just did. Okay, you guys, T minus 8 minutes, we can do this. We're going to do one more example. I hope that that made sense for you guys. We're going to do one more example here, okay? Just going to do some erasing. Ba-da-da-da-da. Keep on erasing. But anyways, yeah, so while I'm erasing this, I'm just going to basically reiterate what I was saying, which is that we're here to help you guys. Whether or not you end up, like, you know, coming back every week, you're more than welcome to come back every week. And we do have kids who have joined us each week since we began. And I do think that is the most conducive to understanding everything that we're going to be doing, because we are going to try to do things pretty sequentially. And so if you do miss 1 week, it'll make it a little bit harder for you to pick it up the week after. That being said, we are going to try to keep recording these. Like last week's is up on our YouTube channel. So you are welcome to take a look at that if you want. And this one will hopefully be on the YouTube channel as well. So let's do another question. Let's try something a little bit harder. We've got cosecant of 11 pi over 3. Well, there's a lot of different ways that we can do this. What I would first recommend is changing this to a pi by 6 model. So I'm going to multiply the top and the bottom by 2, which is going to make it 22 pi over 6. Okay, you guys. So the reason that I did that is because it's going to make the rest of this stuff a little bit easier for us, and we can figure it out a little bit faster that way. So let's kind of think about this. How many times does 6 go into 22? Well, we know that 6 goes into 18 3 times. So that means we're going to literally be able to go around this 3 times. So that's going to be 6 pi and then all the way around. So here we are. 1, 2. Yeah. Okay. So basically we know that 6 goes into 24 perfectly. So here we're going to basically take a look at this. We're going to change these in terms of 6. Okay, guys? So this is going to become 3 pi by 6 because I'm multiplying the top and the bottom by 3. This is going to become 6 pi over 6. This one here is going to be 9 pi over 6. Okay? And so on and so forth. So here we've got, instead of 2 pi, it's going to become 12 pi over 6 because that's the same thing as saying 2 pi. And that means that we've been able to, by 2 pi at 12 pi over 6, we've actually gone over once. So that's 1. And then again, a second time. So now this is going to become 24 pi over 6 because that's the same thing as saying that you went to 4 pi. Now, the reason that we're using 24 pi over 6 is because we're actually going to be in this quadrant here with our line. So let's pull this up here. Let's use a different color. I just hate red because I always associate red with being wrong. So let's do, I don't know, green. You guys cool with green? I hope you are. So here we go. This angle that we're discussing is going to be in this quadrant. And we know that because 24 pi over 6 is basically like saying 4 pi. And basically we have 22 pi over 6, which means that it's got to be in here. And we're just going to minus 2 pi over 6 to get 22. Oh, that's not what I wanted. Here we go. To get 22 over 6. Okay, you guys, so that means that the angle that we're going to care about is pi by 3 because to get from, let me just show you guys. I'm going to illustrate what I'm talking about because I know that it sounds kind of insane. 2 pi over 6. Well, that means that we're here, right here in this quadrant 4. So with our 2 pi by 6, another way of saying 2 pi by 6 is actually pi by 3, which is really another way of saying, oh, sorry, just dropped something, which is another way of saying 60 degrees. And we know the 60 degrees, pi by 3, we know that that is part of one of our standard triangles, and it's actually pretty easy for us to solve, okay? Now, let's go ahead and do that, because I know we're running out of time. So here we go. We've got this angle, which is pi by 3 right here. And we care about all of this stuff. So again, using our standard triangles, we know that with a 90-degree triangle where we have pi by 3, we have the opposite is root 3, the hypotenuse is 2, and this is 1. And this is, again, a standard triangle that I highly recommend you guys memorize. Okay, so if we've got pi by 3, this one is pi by 6, and this is 2, this is root, this is root 3, and this is 1. This is something, again, I highly recommend you memorize the 2 standard triangles, because once you know the 2 standard triangles, you know the entire unit circle, and you don't have to memorize anything else in the unit circle because everything relates to these 2 standard triangles. Okay? Alrighty, guys, let's wrap this question up here because I'm sure you're getting sick of my voice, and I know I'm getting sick of my own voice. So let's do that. So the point here, this point, we can also call this 1 and negative root 3. But more importantly, we know, I'm just going to erase some stuff here so we can make space. More importantly, we know that cosecant is the inverse of cos. No, of secant, not cos, of sine is what I'm trying to say. But keeping that in mind, we know that sine of theta is opposite over hypotenuse. So cosecant of theta is hypotenuse over opposite, obviously because it's the inverse. And in that case, that applies all the time when we're looking for cosecant. So keeping that in mind, let's look at what the opposite and the hypotenuse are here. So the opposite of pi by 3, the side length is root 3, and the hypotenuse is going to be 2. And we can just go ahead and plug those in, 2 and root 3. And that's a negative root 3, so this whole thing is going to become negative. And we're going to rationalize this by multiplying both sides by root 3, because that's what's in our denominator, and we don't like radicals in our denominators. And the final answer is going to be this. Oh, not that. Let me just fix that. Okay, you guys, a couple things I want to note here before we go, because it's past 6 o'clock now. First of all, if you know your standard triangles and you know them really well and you've memorized them, everything comes so much easier to you. This is all just about manipulating numbers and understanding that one thing in particular about the unit circle is that the unit circle, using the cast rule, is really complicated to understand. Instead of memorizing the cast rule, because in my opinion, it's not the most effective way of understanding the unit circle, instead understand that cos is x and sine is y. And it follows the same rules as the Cartesian plane. So, you know, in quadrant 1, x is positive, y is positive. Same with cos and sine. Here you've got negative x, positive y. Here you've got negative, negative. And here you've got positive x, negative y. So if you look at this here, it makes sense that we had a negative y, because this here, this side length of root 3 has to be negative because it's going into the negative y direction. Okay, you guys? So anyways, I hope that this was helpful. If you guys have follow-up questions, or if you have questions that you want us to address during next week's live stream, send them to our email address. Our email address is admin@scholarlyelite.com, or you can go to our website and just submit a message there. That's another way that it'll come straight to our email address, admin@scholarlyelite.com. You don't have to send questions about trig. They can be about anything having to do with the advanced functions course, and we will address them during next week's live stream. But let me move this up a little bit. But until then, I wish you guys all the best of luck in doing your math. I hope that you guys are healthy. I hope that you're safe out there, and wishing you guys all the best, for real. And if you have any questions, like I said, submit them to our email, admin@scholarlyelite.com. I'm going to go take a 5-hour nap now because I've been talking for like 6 hours straight at this point. But I hope you guys are well, and I'll talk to you next week on Thursday, same time, same place. Okay? Have an awesome day, and see you soon. Bye.